Snell's Law. How does it help us learn about refraction, and how do we apply it? The difference in angle between the medium of air and the glass in this photo is caused by refraction. Interesting mathematical properties make refraction predictable and useful. To briefly define, refraction is the change in the direction of a wave as it passes into a different medium. What Snell's law calculates is the angle of refraction when given the angle of incidence by using the fact that the sine of these two angles are an equal ratio to the speed of light in each medium and or to the refractive index value of each medium as a reciprocal. Let's apply the equation of Snell's law to a real example. In this case, the angle of incidence is unknown, and that is what we are solving for. We know that the light enters the new medium of water from the medium of air, leaving at an angle of 20 degrees. The sine section of the equation can be substituted with this knowledge. Next, using the refractive index, or table of pre-observed values from different mediums in which tells us how much light is slowed. For our mediums of air and water, these determine the speed of light by dividing 300,000 kilometers, or the speed of light, by the corresponding refractive index number. The ratios we get here are the same as just taking the ratio of the reciprocal and the refractive index, however, which derives the most common form of Snell's law. By cross-multiplying the angles of refraction and the refractive indices, you are left with the equation on the right. Now, if we plug in numbers from the example into this equation, and then solve algebraically, we should be left with an angle of incidence of 26.1 degrees. This means that the light hit the water at 26 degrees and then changed direction to an angle of 20 degrees. It's intuitive why light travels slower in a denser medium, but why does it change direction? If you imagine light as a car with 4 wheels, there will be a time when one wheel is in the slower medium, but the rest are still going at full speed. Thank you for listening, and I hope that Snell's law makes sense to you.